moderator is Şener Oktik. He is from the Faculty of Engineering and Natural Sciences. And our discussant is Dr. John Bowlus, and he is also a member of the CESD. And okay, dear professor, screen is yours.
Okay, Sally, thank you very much for introducing us. Hi, John. It looks that we are going to go hands in hand to really complete this session, but it looks very interesting papers in there. I think if you have anything to say, otherwise just start really just the first one.
That sounds good to me. Yeah, it does look interesting. Okay. We'll learn something today.
Okay, for today's, the first one is on the effect of alkaline pretreatment on the biomethane production of hemp Hurd. This is by Alfan Can Arıç, Sadık Can Karagöz, Tuğba Ceren Ögüt, and Tuğçe, Dağlıoğlu, Gözde Duman. Or quite a long distance, Jalianek, Nuri Azbar, and they are from Aegean University. We are all ears to listen to you. This screen is yours. Thank you.
Thank you, Professor. My voice is okay?
Yes, okay.
Okay, thank you. Now I'm sharing my presentation. It's okay?
Yes, but you can bigger.
Now, yes.
Okay, then that's better.
Okay. Hello, everyone. My name is Tuğçe Dağlıoğlu from Ege University. Today, my presentation is about impact of alkaline treatments on biogas production of Hurd. Hurd is actually a waste part of hemp. And firstly, in my presentation, I introduce hemp, what is hemp, and Hurd also. Then I will tell our methodology, and after that, I will share our results, and finally, I will finish with my conclusion. First of all, I would like to introduce hemp. Hemp, in Latin name Cannabis Sativa, is an annual herbaceous plant, very special plants actually, and it belongs to the genus Cannabis under Cannabinaceae family. Cannabis sativa is an industrially productive strain and can be used for its fiber, its biomass seed, and also oil production. It's very important because fiber plants contains high cellulose and lignin and used to obtain long and durable fiber. I said before, hemp is very special plant because each part of hemp is valuable and can be used commercially. You can see here parts of hemp. If you start with hemp seeds, you can see here it's used for seed and also oil and hemp seed meal. Flowers used in pharmaceutical industry, cosmetic industry. Fibers is very important for textile and paper industry. Roots used for phytoremediation and soil revitalization. And in our study, we use sheaves. Actually, in this study, in our study, we use the other name of sheaves, Hurd. And after all of my slides, I used Hurd, and it's used for animal bedding and constructive materials. You can see here. To understand the structure of hemp, maybe it's more, we can look at this sham and we can understand more detailedly, because the outside of the hemp bark is, it's called as bark, And inside part, it's called stalk. Stalk consists of two parts. One of this bast fiber and the other one is hurd. You can see here. Hemp hurd is more woody part of hemp. It's used in paper industry, building material, and in our subject, bioenergy production. Hemp hurd is also lignocellulosic biomass, and lignocellulosic biomass consists of hemicellulose, cellulose, and lignin. These parts very important for producing biofuels. And how it is carried out? Let's look at here some bioprocesses. Bacteria and other microorganisms have some metabolisms such as hydrolysis, acidogenesis, and others. And after their metabolisms, they produce for us, for people, biofuels such as bioethanol, biomethanol, biogas, biomethane, hydrogen, and biodiesel. Lignocellulosic materials is very available, economical, sustainable. Yes, have very good advantage. But in chemical structures of lignocellulosic biomass, we have to consider that they include some lignins, hemicellulose, and cellulose. These parts can be problem for microorganisms to produce, but when they produce biofuels, because they are very big molecules and they need some pretreatments to get little molecules, monomers, we can say monomers, so the microorganism can use monomers to produce biofuels. Here, in parallel of all these knowledge, in this study, we aim to compare the anaerobic digestion, and the other name after anaerobic digestion, we produce biogas or biomethane, we can say. So to compare the AD performance of Hurd pretreated with alkali, sodium hydroxide and potassium hydroxide, and thermal, to observe the structural change after pretreatment methods, to valorize the waste part of industrial hemp plants, to apply the influential kinetic model to Hurd methane production. And our methodology. In our methodology, first of all, we start with Hurd, our raw material. Hurd, we supply our Hurd from Samsun Black Sea Agricultural Research Institute. And we use two varieties of hemp Hurd. One of these is Narlı Saray and the other one is Futura, you can see here. And before the transport and before the experiments, the Hurd was cut into 5 to 6 millimeter pieces, and we use grinder for cutting them. And you can see in this slide our sham, our pretreatment sham. We use sodium hydroxide and potassium hydroxide and thermal, only thermal without any chemical treatment. Here you can see the centigrade and our times 20 and 60 minutes. And the third one is alkali plus thermal. You can see here. These are the same with thermal, and just the difference is that we use chemically and alkali, sodium hydroxide and potassium hydroxide. After this pretreatment, we forward the next step, BMP, biomethane potential step. Here you can see the inoculum here, inoculum, an anaerobic part. After is added sample here, raw material and pretreatment material, Hurd. and then water and nutrients, and here are space for gas. Pretreator was added to bottles and there's total solid in 1 gram. Also, each bottle contains 50 milliliter inoculant, 1.5 milliliter basal medium, and control groups prepared parallel, only 50 milliliter inoculant and only basal medium. And we use GC for analyze the gas content. Also, we apply kinetic models. We use 2 kinetic models. The first order kinetic model, the other one is modified comparison model. Here you can see that in this part. And after treatments, our results here you can see here. I can explain. As I said before, we use 2 different chemicals, sodium hydroxide and potassium hydroxide, and we use 2 different varieties of hemp hurd. The blue ones are narlisarai and the orange ones are futura. First of all, we look at the raw hurd. We see here narlisarai is little better than futura, but after treatment, futura had better than all of the three type of pretreatment methods. In thermal, it produced 184 milliliters biomethane. In sodium hydroxide plus thermal, futura produced 272 biomethane, and in potassium hydroxide 222 milliliters biomethane, you can see here. Yes. And we also carried out an experiment to understand the chemical structure of hemp hurd. I mean, after pretreatment, what happened? We need to understand this because our sodium hydroxide is the best, but how? And in chemical structure analyze, after analyze, we see that narlisarai crude hurd and futura crude hurd really increased. It's very good seen here. Narlisarai and sodium hydroxide, here you can see, and also narlisarai, futura sodium hydroxide and potassium, very good increase in cellulose percentage. And also hemicellulose degradation can be seen here. It's very parallel our biomethane production results. And other kinetic models, we can say that first order kinetic model and modified comparison model show difference 0 to 11% and 0 to 13% between the measured predicted methane yield. This deviation caused by the different characteristics of models and biological activity, especially lag phase in comparison model. Since lag phase was observed in some of the trials, the modified comparison model fits better for them, and combined with alkaline and thermal experiments where the higher yield was observed, the modified comparison model was best fitted in this study. As a conclusion, in this study, the BMP of hemp hurd of narlisarai and futura varieties and the effect of chemical pretreatments were investigated. The results demonstrate that alkaline pretreatment with thermal application increased the BMP of hurd of 2 varieties. The obtained results were similar in the sodium hydroxide and potassium hydroxide pretreatments, but sodium hydroxide is more economical, the inhibition effect of sodium ions should be considered. Potassium hydroxide should be evaluated in terms of fertilizer, potential of digestive potassium content. All the Futura had a higher BMP than Nardisaray. The energy potential of Nardisaray, a domestic variety, was higher when its harvested yield was considered. The Hurd, which is the waste part of hemp, is imported in future studies to evaluate the waste part of the diverse and valuable part of the plant. And in the part of the session, you mentioned many names. I've joined to our teams here. You can see it's actually a big, very big TÜBİTAK project. So our team very crowded. You can see here. Thank you. First of all, thank you, my team, my laboratory team, and also Professor Alvar and Professor Yanık, our supervisors, and also thanks TÜBİTAK for financial support of this study, and thank you.
Okay, Tuğçe, thank you very much for this presentation. Tuğçe, actually this very interesting. As you know, what you are dealing with hemp is one of the natural polymer. And you were dealing with two different sources for the same polymer hemp, and you got the different results. Is there any difference in the actual structure of the molecular length? What is the main difference fundamentally between two? Is it because of the contaminations in your herd, or what was the reason?
You asked between sodium hydroxide or
Yes.
hydroxide or
no, hemp itself. You got one.
Sorry.
You got Narlısaray and others.
Yeah.
And you saw some difference in the actual yield.
Actually, they harvested the same place. They harvest, their dry matter is same, their cellulosic structure is very similar, but the difference here,
Yes.
we interpreted that actually our research is going on now because it needs more analyzing such as photospectroscopy like this, because to understand the linkage between lignin or between carbon-carbon linkage like this. So we now going on the our experiment to understand better, but we also talk about Samsun Agricultural Institute to understand why difference is, but finally we thought that the Narlısaray is local variety, and Futura is genetically modified from French. So
That's what I was really trying to say. Probably it might be helpful to really give the structure of the molecules. It's a macromolecule of that polymer, that's a natural polymer. It might be helpful really for us to see what's the difference that two different kind of polymer of. Do you know anything, or do you have any models to show us? It will be quite useful for the listeners to imagine really where the difference is coming from.
I got it. Thank you for your comments.
Thank you very much. John, please take you to the next one. Thank you very much.
Sure. I mean, I'm not a chemist. I haven't taken chemistry since high school, I think. So, you know, I have nothing kind of quality to say or ask, but I find it, the project very inventive and interesting to apply this to energy and as part of kind of the clean energy transition and a more sustainable environment, and using our resources to their full. You know, I know the Western experience too, just, you know, only recently have they kind of come back that hemp is legal again, you know, so really it was a silly many decades that was lost by not using the plant. That's very useful for a more sustainable life. So I just applaud the scope. You know, that it's a new phenomenon. Obviously, Turkey's looking into it commercially and to develop it. So I just applaud the project. I think it's great.
I do congratulate all of you in the team. Thank you very much for the presentations of your group. Thank you. John, you can introduce the next one, please. Carry on, we can go one by one. Your microphone is, John, your microphone is now on.
Thank you. I don't have the next one in front of me, whereas I didn't realize I was going to be,
okay,
okay, I can bring it up now. It's coming now. Okay, so the next we're going to have the conversion of hemp waste to solid fuel. Wait, right? Is that the next? That's the next presentation?
Yes,
maybe.
Yes,
okay.
Right.
Because we have a very similar category. Müzeyyen, Eser, Peker, Gözde Duman, again Tuğçe, Dağlıoğlu, Nuri Azbar, Jala Yannick, and they're all from Ege University. So this will build on our last presentation.
Conversion of hemp to solid fuel. Hemp and hemp. Industrial hemp has a place in industrial plants. Waste as a hemp plant has rich organic matter. And industrial fiber industry has many uses of industry. Biopolymer, geotextile, construction materials, and energy. Energy production from hemp can be like two ways, like biochemical conversion and thermochemical conversion. In the biochemical conversion way, anaerobic decomposition to obtain methane to hydrogen gas, and also thermochemical conversion means pyrolysis, hydrothermal carbonization, gasification, and combustion. Hydrothermal carbonization is our subject in this project. Energy recovery from hemp by thermochemical methods, how it's going. Raw herd and digestate goes through hydrothermal carbonization, and two products are produced: hydrochar and processed water. Hydrochar can be used as hydrogen gas by gasification, and also can be used solid fuel. Processed water can be used wet fermentation. The aim is in this project obtaining hydrochar from hemp and digestate by hydrothermal method and using it as fuel with approach. Thermochemical conversion that used is hydrothermal carbonization. Like wet biomass goes through hydrothermal carbonization reactor and then goes with hydrochar, the main product. What is hydrothermal carbonization? Hydrothermal carbonization is a thermochemical method that transforms biomass with high moisture content into hydrochar with high heating value at low temperature. What is the parameters that affect hydrothermal carbonization is temperature, time, pressure, biomass type, biomass water ratio. The feedstocks in this project, raw hemp and dry digestate fermentation. In the raw hemp side, there is Narlısaray 19 and also Futura. These two has 5% moisture content, and dry digestate fermentation, Narlısaray 19 digestate, dry digestate, and also Narlısaray 19 pretreated with sodium hydroxide. Moisture content is 8%. The analysis we use for the processed water, hydrochar, we do in this experiment, we are doing the hydrochars analysis, so elemental analysis, proximate analysis, and component analysis.
Also, processed water can be analyzed with COD analysis and phenol analysis. Parameters in that project: temperature, we try to keep like 200, 225, 250, and 275. And time we took 1 hour and 4 hours. Biomass water ratio is 10 to 100 and also 15 to 100. Biomass type, as I mentioned before, Narlısaray 19 Futura, Narlısaray 19 dry digestate, Narlısaray 19 dry digestate, pretreated with sodium hydroxide. And we are going with results. The effect of it's the Narlısaray 19's results, that effect of temperature, time, and biomass water ratio and hydrochar mass yield. As you can see here, the temperature increases, mass yield will decrease. And also, there was no difference between mass yields obtained at duration of 1 hour to 4 hours. Can you see my mouse in the screen?
Yes, yes, we can see.
Yeah, okay. And also the biomass water ratio is over there. Doesn't make any big differences at all. Effect of temperature and biomass type on hydrochar mass yield. In this figure, the effects of biomass type and temperature on mass yield was comparatively given. As mentioned before, the increase in the temperature led to lower the mass yield, and the mass yield of hydrochars obtained by Futura and Narlısaray were almost same for each temperature test. You can see it here. On the other hand, the yield of digestate derived hydrochar was found to be higher than that of corresponding biomass. As we can see here, for Narlısaray 19, carbon and fixed carbon contents of hydrochar were, you can see here and see here, were increased with the increasing temperature, while volatile matter is decreased. Energy yields decreased with the increasing temperature due to low mass yield at higher temperature. And I'm so sorry. When we come to the Futura, there is a similar result as the Narlısaray one. The temperature increasing and also mass yield is decreasing. Also, the increasing temperature carbon content is also increasing. And now we have a problem here that ash contents are going increasing. So interesting that ash content of the hydrochar derived from Futura is increasing with the increasing temperature and higher than that from Narlısaray 19. Inorganic content of Futura and Narlısaray 19 may be responsible of the difference in the ash content of corresponding hydrochars. ICP results show that Futura derived hydrochars had high amount of aluminium and also ferrium, which were insoluble during hydrothermal carbonization process, and iron and aluminium concentration were continuously increased with the increasing temperature. 0.58 and then goes through 6.10. And also the energy yield decreased with the increasing temperature due to low mass yield at higher temperature. Same with the others. Narlısaray digestat, dry digestat, mass yield also decrease with the increasing temperature. Yes, you can see. Sorry. Comparing the Narlısaray biomass and hydrocharged digestat has higher ash content. This unwanted increasing of the ash content caused by inculum used during the fermentation, which has a high amount of inorganic. You can see here. Inoculum that used for fermentate the Narlısaray. The ICP analysis of Narlısaray dry digestat and Narlısaray dry digestat hydrocharged and the inculum given in that slide. The ash content of inculum was 30%. Sodium, potassium, magnesium, calcium, aluminium, and iron, which are inorganic elements originating from the inoculum, remained in the structure of the Narlısaray dry digestat. Comparing all of the hydrocharge, it was observed that most part of sodium and potassium were dissolved during the hydrothermal carbonization. On the other hand, major part of the magnesium, potassium, aluminium, remained in the hydrocharge, particularly in Narlısaray dry digestat 250-25 and 1 hour, and Narlısaray dry digestat 250 1 hour, which caused the higher ash content. And also the energy yield decreased with the increase in temperature due to low mass yield at higher temperature. And again, the increase in temperature, the mass yield will decrease caused by that. As we can see here, Narlısaray dry digestat sodium hydroxide pretreated one, carbon content increased by the increasing temperature, and the ash content increased by the increasing temperature, and also the fixed carbon is the same. The energy decreased with increasing temperature due to low mass yield at higher temperature again in this subject. And here is a van Crevelen diagram that are samples. According to van Crevelen diagram, except for 250 hydrocharge of Narlısaray and Futura, all of the hydrocharges are in the same position. Yeah, here. Hydrocharges that 200-degree positions are still in the biomass site. Yeah, here. Narlısaray 225 and Futura 225 hydrocharges were come up to the turbo site. And Narlısaray 250 and 1 hour is close to the lignite site. The hydrocharge that produced in temperature at 275 and Futura 250 and 1 hour were in the cold position, as you can see here. Increasing in the temperature hydrolysis, decarboxylation, and dehydration reactions cause oxygen and carbon ratio and hydrogen carbon ratio decrease. Dehydration reaction is more dominant in Narlısaray type Hurd, and on the other hand, dehydration reactions of temperature are more efficient up to 250 degrees in Futura type Hurd. At 250 and 275, decarboxylation reactions were important. So, ongoing and future works. There will be hydrothermal carbonization experiments for Futura digestate and Futura digestate pretreated, and also combustion properties of hydrochars obtained under optimum conditions will be examined, and water vapor gasification trials will be carried out. So, thank you.
Okay, I'll jump in. Thank you for that presentation. Again, quite interesting. I can't comment on it, but it's in the context, as I said with the last presentation, very productive and cutting edge. And I think I'll pass it to Şener Hoca and see if he has more qualitative things to say here.
Thank you very much. Actually, this I presume this is the follow-up of the previous presentation. It's enormous amount of information there to digest. Honestly, this field is not my field directly, but scientifically, when I think of just this paper is for the larger audience, probably language could be a little bit common. Some definition could be there to make it more clear to understand and to follow. One thing probably might be improved in that this mass energy relationship and the actual efficiency in there related to some of the metals, some of the inorganics within the system. I cannot really catch which one of them are more effective to really in the actual mass energy relationship from starting material to the end product. That might be nicer really to see there. Again, for the both paper, okay, this work is really aiming to have some kind of product for the industry. It might be very interesting to see really what will be the cost of per unit and how can you compare with others. At the end of the day, you're aiming to use it somehow. And probably those points might be improved, I think, if they're not already have the information, some information in comparison of the cost of per unit energy through this process might be quite useful. Thank you very much. It's very good, very interesting. It looks as a very large project, part of the large project. Probably those informations might be somewhere hidden.
Thank you for your attention.
But I do congratulate all of you. It's good, very good work, but plenty of information there. It's difficult to digest. Thank you. Okay. The next one, shall I introduce the next one? Well, actually, the next one is a little bit closer to my heart. Is no, the one after that one is Perovskite is closer to my heart. Next one is the conversion of hemp waste. No, this is it. Yeah, this is the next one. The challenges for commercialization of perovskite solar cells. And this is from ours, Burak Erdogan. I am all ear to listen to you, Burak. The screen is yours. Thank you.
I'm glad to hear that. Thank you. Hello, everyone. I did a literature review last semester for a class project for Volkan Hoca. And this presentation is from that. I'm sharing my screen. Can everybody see?
Yes, we can see.
The title is Commercialization Challenges for Perovskite Solar Cells. My purpose in researching perovskite was to learn its potential and disadvantages in the renewable energy industry. I hope to explain my findings clearly to you all. My content will be as follows. First, I will mention what perovskites are, what perovskite solar cells are, their shortcomings, and my conclusion of it all. Perovskite materials have a wide range of use in the technology industry. Perovskites are minerals which have specific crystal structure. This structure can have different physical properties with different types of elements. This makes the versatile material. Any mineral which has the crystal structure of perovskites can be categorized as a perovskite. The mineral perovskite was first found in the Ural Mountains of Russia. It is composed of calcium titanium oxide. A perovskite has to have two cations. Cations are elements which have more protons than electrons. It also has to have one anion. Anions are elements which have more electrons than cations. It is found in Earth's crust rarely and found in Earth's mantle abundantly. Most abundant type of minerals are perovskites, since all minerals with the same crystal structure with a perovskite is considered one. Mine sites for perovskites can be found in all around the globe. Unfortunately, so far there is no mine site in Turkey. Perovskite solar cells. Perovskites are used as the light absorbers in perovskite solar cells. In the last decade, its efficiency increased from 3.8% to 25.2%. PCSCs have higher efficiency and they are cheaper to manufacture than silicon solar cells. Also, unlike silicon's manufacturing process, there is no gas emission. So why perovskite solar cells are not dominating the market right now? The reason is because they have a lot of shortcomings. First of which, perovskite solar cells have major stability issues stemming from multiple reasons. This ultimately affects the lifetime of a cell. There are currently some perovskite solar panels which can be used for 1 year. This is obviously not enough for it to be used commercially. A drawback to perovskite is that long-term exposure to UV light, which exists in sunlight, creates deformities in its structure. Another point which creates deformities is long-term exposure to high temperatures. PCSCs can be exposed to 50 centigrade degrees. Also, they can be exposed to up to 106.85 centigrade degrees in vacuum environments. But increase of temperature over long term reduces the efficiency of solar cells linearly. These mentioned issues can be solved in the laboratory, but the size of the solar cells in the lab are too small to be used commercially. So this shortcoming can be summed up as a scaling up the dimensions issue. LED. PCSCs, which consist of LED, are impressive regarding their efficiency. They are one of the most, they are one of the best performance having perovskites. But lead is a heavy metal element. Lead is toxic and it can easily dissolve in water, which can cause harm to human health, animal health, and environmental pollution. Moisture can decompose perovskite materials, especially lead ones. This is a result of perovskite reacting with water molecules. Light-dark cycle creates fatigue. Fatigue leads to performance loss. The fatigue is caused by the cycle, which makes the particles inside the perovskite film to make defects on the surface of the material, and these defects create vacancies on the surface. My conclusion from the literature review I have done is that while perovskite solar cells have good performance results, they are cheaper than silicon and better for the Earth overall, it is still a developing technology. Its instability and size problems need to be addressed. So testing of stability and scaling up the dimensions of PCSC need to increase. PCSCs must be able to last for 20 years with minimal degradation. Perovskite has no geopolitical threat since it can be found everywhere, unlike other rare minerals which are used in technological devices. Until then, silicon, in my opinion, will continue to be dominant in the market for solar cell material. Thank you for your attention and time.
Burak, thank you very much. I do agree with all your conclusions.
Thank you, sir.
But I can make a couple of comments probably on this presentation.
Yes.
Possibly, at the beginning, it might worth really putting what is the really total power by photovoltaic, total power of PV in the world, and what's in Turkey. It's a very good point to start with. And of course, you already mentioned at the end how the actual installation in the world are shared by, as you said, almost 90 something or almost 98% silicon than the rest. And how perovskite is coming into the scene last probably 15 years or so. And where is the perovskite you mentioned? It's very good. But the good thing, probably it might be a good part to add the combination of peroxide with others like silicon, perovskite silicon combinations. Then it will be very, just it will improve your feeling and your really effectiveness to the audience. Yes, I do agree. Perovskite is a very good candidate, and recent figures suggest that some companies already start some pilot production relying on perovskite silicon combinations, and the efficiency is now almost 30%. I should really say to you, it's very good. Yes, it's good. Thank you very much. Really bringing perovskite into the into the sort of attention of larger audience. I do thank you and Volkan Hoca taking this on the plate. Thank you.
Thank you for your comments.
Yeah, I echo that what Şener Hoca said. I just had a question, I guess, for the map you showed of where the mines are.
Yes.
I noticed that there are a lot in Europe, if
Should
I
I
read the
share
map
it again?
correctly. If it's helpful, perhaps, because I may not be reading the map correctly.
Sorry.
So I guess I'm wondering if what are they mining it for? I mean, what other uses are they?
I mentioned in the slide there is a lot of technological fields which perovskites are being used right now, especially in electrical engineering fields like superconductors, piezo ferroelectric applications. They are even used in medical industry like biomedical industry, also battery applications. So these sites are generally used for those purposes. There's a lot in Germany, especially in Canada, in Africa, in China, in Russia. So I took this picture from a site which gives you nearly a lot of mineral mine sites and where they are and if they are being currently used or not, or when did they open. It gives detailed information about mineral mine sites. So I took perovskites from there, and there was no Turkey. Yeah.
I'm sort of jumping into John's questions, but when you really put this map on the screen, it's not clear. This is the number of sites. Probably it has to be, and probably most informative would be really what is the actual potential capacity per year, per tons, just it might be quite informative. We're from all those sites, what is the total perovskite mineral extracted per year per tons. This could be improved. Sorry for really jumping in your question. I'm sorry, John.
Yeah, no, I mean, I'm just, you know, from a kind of geopolitical angle, what, you know, I mean, yeah, maybe there's one huge mine in Russia, it sounds like, even though it just lists 10 on the map, maybe one of them is just so big. I don't know. Yeah, that is an interesting point. And of course, all this is interesting just with kind of will be interesting in the next coming decades with the clean energy transition and kind of this whole, you know, shape of critical minerals and, you know, the dependence on, you know, at this point, China has such a grip, not so much, I mean, they have a lot of the production, but it's the processing that they have a, you know, an 80% hold on roughly. So, you know, kind of that's the geopolitical angle that can come into all these technologies that use various minerals. And there's so many minerals, so it's studying energy is kind of going to be more and more complex in this regard to kind of put the minerals in each of their silos and who has what and etc. So I think it's a useful, and I did not know about perovskites before your presentation, so I appreciate this. Thank you.
Should I stop sharing?
Yep. John, next one is yours.
Professor John, we cannot hear you.
Thank you. I mute too much. So the last presentation we have is by Mahmut, Cüneyt, Kahraman from Yalova University. It's entitled "The First Nuclear Power Plant in Turkey, the Akkuyu Nuclear Power Plant," which I'm looking forward to hearing about. So the floor is yours, Mahmut.
Hello, everyone. I hope you can hear me and see my screen.
Yes, we can see.
Okay. Good afternoon, everyone. First of all, I would like to introduce myself. I am Mahmut Kahraman. I'm doing PhD at Istanbul Technical University about molten salt reactors, safety systems, and at the same time, I work as a research and teaching assistant at Yalova University. My presentation will be about Akkuyu nuclear power plants and what I will talk about. Firstly, nuclear history of Turkey and Akkuyu project agreement and technical properties, and the agreement details built on operate project type. What is it? I will give a brief explanation about it. And so what is the concerns, what's the learnings and earnings of Akkuyu projects? And finally, I give this information about Akkuyu project that public knows but is not correct. So what's the nuclear history? How the nuclear history of Turkey started? In 1956, Turkish Atomic Energy Authority was founded, and in 1957, Turkey became the member of IAEA, and in 1962, first research reactor Triga was started its operation in Çekmece, Istanbul. And in 1972, 7 different areas are determined, and Akkuyu was selected as the first nuclear power plant area. And but during that time, because of some political reasons and also the negative effect of the Chernobyl nuclear accident, the projects will not be implemented in that time, and many years passed, and finally in 2010, between Turkey and Russia signed an agreement of intergovernmental agreement to build a nuclear power plant in Akkuyu in Turkey. So in 2018, the construction of the first unit started, and in 2020, when we came to 2020, we know that Unit 1 and Unit 2 construction works already going on, and according to construction licenses. So what is the agreement and details and what is the technical properties of these projects? So this is an intergovernmental agreement signed building of 4 units of nuclear power plants between Russia and Turkey. And so the project developed under BOO model, BOO build on and operate. I will give an explanation on the following slides about it. And the project estimated cost around $20–25 billion. According to the last news I get it, is around, yeah, it came to $25 billion now. So in this agreement, there's another agreement, purchase power agreement, and it will, the duration of this agreement is 15 years. According to this agreement, first unit and the second unit of the electricity has to bought by Turkish authority as 70%. And the units 3 and units 4 is the same, but it's the 30%. So the remaining electricity can be sold within markets by the Russian side. So what is the electricity prices? And Turkish authority has granted that they will buy the electricity from the Russian side, 12.35 cents per kilowatt hour. So also there will be a payment for 0.15 cents per kilowatt hour during the power purchase agreement for the Waste Management Fund. So when the power purchase agreements finish, 20% of the net profits will be transferred to the Turkish government. I mean, after 15 years. So what about the responsibilities? Because this is an agreement and two sides has some responsibilities. Turkish side responsibilities are providing Akkuyu site, okay, and the grid connection of the Akkuyu nuclear power plant, and to buy the electricity according to the power purchase agreement. So what about the Russian side? Russian side has to provide the capital for this project, obtaining all permits and the licenses from Turkish authorities, commissioning of the power plant, supplying equipment, especially for nuclear fuel, and provide operation and the maintenance of the nuclear power plant, and waste management and the commissioning of Akkuyu power plant after its life's end. And the technology, I think these last two important points, that technology transfer and exchange of information from Russian side and Turkish side, and also training of Turkish students and staff of Akkuyu power plants. As we know, a lot of Turkish students goes to Russia to take a bachelor and a master training, and then they come back to Turkey and work at Akkuyu power plants. So what about the technical properties? We talk about the project that is 4 units of the power plant, each of 1,200 megawatt electricity, and is a water energetic reactor. It means that the cool water is a moderator, at the same time is a coolant. So what about the lifetime? It's expected to be 60 years, but according to our experience, it can be extended. So Akkuyu nuclear power plant produce about 35 billion kilowatt hour per year. And according to projections, it will provide 10% of Turkish electricity needs. So as we see here, the first construction started 2018, and the start operation of the first unit will be in 2023. And the other units will start operation on the following years. So I want to give a detail about this project type because it's the first in the global nuclear industry built, own, and operate. Under this model, the supplier, I mean the Akkuyu Nuclear GSC, is a new company, is founded by the Russian side, is the investor and also the owner of the projects, and gaining the returns on investment during the operation from power purchase agreement. So Akkuyu Nuclear GSC is the project owner in charge of MPP design, construction, maintenance, operation, and the commissioning. So when we look at the final shareholders of the company, we see all these the Russian side, and the high percent of the shareholder is the Rosatom, that's the Russian company. So according to the agreement, Rosatom will have the minimum 51% of Akkuyu nuclear GSC shares. So the rest can be sold to investors, to Turkish side or Russian side or other any companies. But the minimum 51% means that the owner of the company will be the Russian side. So what about the concerns about the project? Is the first nuclear power plant? Is there a new type? The agreement? So are there any concerns? And I think we have some. So the political problems between Russia and Turkey, I think affects the nuclear projects. And it may cause some delays in the project, as we experienced in 2015, Russian aircraft shut down, and the nuclear project had some delays in that time. So also another issue is the price competition of Akkuyu project. According to the agreement, Turkish side has to buy electricity in the price of 12.35 cents per kilowatt hour. So when we look at the other energy sources like solar, wind, and coal, the prices looks a little bit lower. And yeah, it's hard to talk about it now because we don't know after 2023 electric prices go up or down, but we have to consider these prices for the following years. Another issue is the nuclear safety culture in Turkey. We didn't have experience in this field in nuclear sector. So I think we have to create a nuclear safety culture in Turkey. It's an important issue. And the advantage of one of the advantage of this project is that Russia will provide their experience and their safety culture with us. So what about the learnings and earnings from the project? So we will increase knowledge and we will provide technology transfer from Russia. Russia is very well experienced in this sector. So it will increase the job creation for the region and for general Turkey, especially for the nuclear engineers and for also construction workers. So it will stimulate localization for the following nuclear projects. We will get the experience, and our local companies will also have experience for the following projects. And also it will provide energy supply security with a clean energy, especially is so important after we sign lastly, parts agreement. We have to provide carbon-free, clean energy. So nuclear is totally clean energy. So another issue is the project provides the experience nuclear safety and security with the limited risk and the human error, because Russia is very well experienced in this sector. So Turkish companies can increase their work, especially in the construction works. It also provides the experience. And according to the agreement, we are sending our students to Russia, and it will increase the number of qualified nuclear engineers in Turkey. Now 142 Turkish students already graduated from nuclear engineering programs in Russia and started working in nuclear Akkuyu project. So I would like to finish my presentation with this information about the project, because I know that many people don't know the details and there are some disinformation about the project. So I would like to summarize my presentation. Actually, is the owner of the Akkuyu is not Turkey, is owner Rosatom, is the Russian side. And after 15 years, Turkey's agreement ends. Akkuyu power plant will belong to not Turkey, will belong again to Rosatom, because in Turkey there are many projects that the private companies build, and after some years the government get the project. But in this case, is not the same. So Akkuyu is the first national nuclear power plant or national energy of Turkey. Is not really easy to say it, because the maximum localization of projects is expected 40%. So it's not really national project or national energy. So the commissioning is responsibility of not Turkey, the commissioning is responsibility of Rosatom. And spent fuels, another issue, is the responsibility of not Turkey. I mean, after we use these fuels in the nuclear power plant, Russia's side has to consider this issue, and this is the responsibility of them. So nuclear energy doesn't emit carbon, is not it doesn't emit carbon, is a totally clean energy. So what about the earthquake? Earthquake is not a safety issue for Akkuyu projects because its design can withstand earthquakes of magnitude 9. So that's all my presentation. Thank you for attention. If you have any questions, I'm pleasure to answer all.
I mean, thank you for the excellent presentation. Very clear. I like how at the end you kind of debunk, you know, the popular things that misconceptions that people have out there about the project. It's interesting. I would say also I was kind of wondering your timeline of this, if Fukushima was kind of a setback as well for it. You talked about from 15 the jet incident, but that 5-year period there, did that play a role in kind of postponing work, or was it other problems?
Could you repeat this last part? I couldn't get the last part. What did you say?
I mean, you gave a kind of a timeline of the project. That 2010 was when, you know, the agreement came, and then, you know, it got postponed in 2015 because of the plane incident. But I'm wondering, did Fukushima play a role in kind of that 5 years from 2010 to 2015 at all?
Yeah, also Fukushima affects, of course, not only on Turkey, on a global nuclear industry. It was affected by Fukushima accident, but this agreement was already signed, and of course it affected the projects. What I was trying to say in that nuclear, okay, I'm going to back that part. The political, because when we look at the agreement between the countries, I mean, this nuclear power plant agreement, we saw that some issues are not really clear. So is really trust the governments each other, Russian government and Turkish government. And there are some issues are missing on the agreement, and they just trust each other and they sign the agreement. It could be problem, but hopefully it didn't. Only there were some delays in due to Russian aircraft shutdown. But when I talked to engineers from Rosatom, they believe that they complete the first unit and they will start operation in 2023 as planned.
Good, thank you.
Cüneyt, thank you very much. May I take the floor? Okay. That's a quite nice flow on the points of our dance with the nuclear energy. As you know, it's almost more than 60 years story with the nuclear energy power stations. And we are getting close to the end, at least one of them to be a reality. But I'd like to comment a couple of things. When you classify the nuclear as a clean energy, probably we should really classify as an impact to the environmental issues and impact on the human and the living things. When you put it there, how clean is any of those energy sources and the conversion technologies are discussable. Put the nuclear within this context, probably, when you say clean, you are really cleaning the whole idea about the nuclear concept. Probably might be a little bit careful on this. And you have to put really all the possible impact to the environment and impact to the human health. And of course, as you say, that at the end of the lifetime of any nuclear power station. The other thing, of course, the cost. When you put the cost down for different one, for instance, you might be following quite closely the recent figures on the YECA competitions for solars and the wind. They are much, much lower than the 7.9. We are talking about a couple of cents per kilowatt hour. So how we are going to really have that burden on us for 15 years paying, when you say 12 something per kilowatt hour plus tax, there's actual transportation is not in there yet. And probably you have to revise this cost, current cost of alternative ones. Might be helpful really to improve the presentation. The one thing really that something amount $0.15 cent for the water cleaning or something you put there.
That's management, you mean?
No, not the one. For the nuclear power station agreement, there was some allowance for $1.15 cent per whatever tons of water or something for the affluent.
The price for the electricity is 12.35 and one more.
Oh, yeah. Just go one back. No, not that one. Anyway, I did not get that one clearly, really. Who's going to pay that money?
You mean for the waste management? I didn't get, sorry.
Yeah, the waste of water waste.
It's not a water waste. It's a waste management fund. The Russia side.
Yeah, the fund. Who's going to funding that?
Russian side, Rosatom.
Russian side is funding.
Yes,
that. Okay.
yes,
okay.
Not Turkish side.
But apart from those, it was very clear really to put who's owning really, who's the golden share of this process and this power station. Thank you very much. It's quite good work. Thank you, Cüneyt.
Okay, I would like to give a comment about your first comment actually. Why I'm saying the nuclear is clean energy, because when we look at the environmental problems of the energy sources today, we have to face that is the big crisis, big chaos, or the problem is the global warming. And the main issue of the global warming is the carbon emits. That's why nuclear doesn't emit carbon. So when even look at the energy source, other energy sources like from natural gas energy sources or the coal energy sources, nuclear doesn't emit any. So as we one of the countries that signed the Paris Agreement, I think we have to combine the renewable energy with the nuclear, just the way to obey the rule of the Paris Agreement. That's why I just say that it is a clean energy. Of course, there are many issues after the commissioning for the waste management, but is totally another issue. That's why I didn't go to details about it.
Okay, Cüneyt, what I did understand what you are trying to say, but it might be much concise, much effective if you say, okay, nuclear energy really does not contribute to carbon emission or something. You know what I mean? So
yeah,
when you say clean, it covers quite a large spectrum of cleanness.
I got it. Okay, yeah.
Probably you should be more specific on what do you mean by that clean. Okay, yeah, it doesn't really add up to the carbon emission, but there's a big but. Anyway, it's good. It's very good. I like the presentation. Thank you.
Okay, thank you.
Professor Şener, we have 6 minutes for this discussion part. If you have any question, we can take.
I'd like to ask a question, if you just let me ask Professor Oktik.
Ask question to me or to the?
No, to the speaker.
Okay, yeah, please, floor is audience, really.
Okay, thank you, Cüneyt, for this very good presentation. You have put the disadvantages and advantages of nuclear power very clearly. But, you know, I was wondering your personal opinion. Do you think it was a good idea for the Turkish government to sign a contract with Russian company for this nuclear power plant? If you consider the overall advantages and disadvantages, especially in a time period when all the Western countries were phasing out nuclear power plants.
Okay. As much as I know, that only Germany is shut down their nuclear power plants, not any more countries. And as we know, the France has already 75% of electricity generation from the nuclear still. They are just have a projection for the future to decrease the percent of their nuclear share on the all nuclear generation, all energy generation. It doesn't mean that they will shut down their nuclear power plant. They will increase other energy sources in total. So as much as I know, that, as I told before, only Germany is going out from the nuclear industry. So for the general, I think it's a good idea to have nuclear projects in Turkey, but we can of course consider the agreement with Russia, because it's not Turkey projects, it's not our nuclear power plant, because it will be a Russian nuclear power plant. And as I said before, if we follow the rules of the Paris Agreement, we have to combine renewable and nuclear together. So only renewable, I think, is not enough, because renewable not providing the energy anytime as we like. So we have to combine one like a base load energy like nuclear and one renewable together. So our projections should be based on this type of energy policy, I think. So
I'm asking your personal opinion. If you were the energy minister of Turkey, would you have signed this contract for the benefit of Turkish people?
I prefer to sign an agreement not like this. I prefer to sign the agreement like Egypt and Russia does. They have already the same project, but in the Egypt case, they will have the nuclear power plant after the construction.
Okay, thank you. Thank you.
Yes, any more questions from the audience? If not, can I use my right as an audience to ask a question? Yeah, Cüneyt, probably you look into very, very deeply. If you take today's technologies in nuclear power, what will be the cost of a kilowatt hour if you consider from cradle to the grave of this technology, including real materials? Is there any figure really you can put down compared to $12.3 per kilowatt hour we are going to pay? What is the actual cost? You know, what are the hidden costs, of course? You should really take into account, but currently, a country like, you know, just Japan or Germany or France has a larger one probably. What is the per kilowatt hours cost in those countries? Do you have any figure for us?
Okay, I didn't have it on my presentation, but I know that is, of course, is the prices is low because they produce their energy their own. That's why they produce very cheap way. And I have some numbers, but I'm so sorry, I don't really remember the numbers now. I mean the prices, but each country has a different numbers because they use another technology, different type of the nuclear power plants. All this affects the prices of the generation of electricity from nuclear. So each country has a different prices, but I can clearly say that it's cheaper than these agreements.
When you say cheaper, half of it, quarter of it, or how cheap?
I don't want to give an incorrect number, but I can share by email if you want later, because I don't really remember the numbers, but I know that is the cheaper. Because it's changed from country to country.
So we are stuck for 15 years to pay that $12 plus taxes and other expenses, plus the hidden costs we have for the future.
Yeah, that's true. But just think that we have to also provide the energy supply security. Our energy demand is increasing each single year, so we have to provide an electricity from somewhere or some way. So I think, okay, I'm not really favor of this kind of the project, BOO, build, own, and operate. I'm not a favor, but I can say that is better than nothing.
Okay, thank you very much. Anyone else for any question? Salih, how much time we have got left?
Our time is left. This is the lunchtime, and we have 1 hour for lunchtime. If you want to, we can finish this session.
On my count, I thank all the young guys around here and Volkan Hoca, all the people really putting this together. This on my account. I don't know, John might say something before finishing the session.
Just very impressive work. I was impressed with the presentations, the clarity. So thank you.
Thank you so much for audience and for professors. Thank you so much, and see you at 2 o'clock. Okay.
Thank you.
Thank you Şener Hocam.
Thank you.
Şener Hocam, Can Hocam teşekkür ederiz.